Hello students, so welcome to part 3 of the lecture series on the previous year gate questions of electronics and communication on the topic network theorems, brought to you by EDAMIGO team. So we have already completed 2 parts of the lecture series, so this is part 3. So let us directly come to the questions. So this is question number 1 of the this part. So we have to find the Norton equivalent resistance of the circuit across terminals A and B. Now since we know that Thevenin resistance and Norton resistance are same, so RTH and RN are same. So it doesn't matter by which method you are getting the answer. So since in this circuit there is a dependent current voltage source that is dependent on the current in this branch, so to find RTH, since the circuit has dependent sources, so to find RTH we will apply voltage V0 between terminals AB and assume current I0 from the source, and RTH will be V0 upon I0. So this method I have already told you in the previous part of the lecture series. So let us draw the circuit again. So it is 2 ohms. This is also 2 ohms. This is 4 ohm. I is the current here. Now we apply a battery, that is V0 volts, and I0 is the current here. So since we can see that voltage across 4 ohm and 2 ohm resistance will be V0, so I can see that I is equals to V0 by 4. Okay, now assuming that this is grounded, so node A, this is also node A, this is also node A, both the nodes are A, will be at potential V0 and V0. Now in the circuit, KCL at node A, so incoming current is I0, so it is put with a minus sign, so we can see that this is incoming current. Now outgoing current here is V0 by 4, outgoing current here is V0 by 2, and outgoing current here will be V0 minus 4I divided by 2, that is 0. Now we know that I is equals to V0 by 4, so minus I0 plus V0 by 4 plus V0 by 2 plus V0 minus V0 divided by 2 is equals to 0. So this term cancels out. So I0 comes out to be V0 by 4 plus V0 by 2, taking 4 as common. So it is 1 plus 2 V0, that is I0 is equals to 3 by 4 V0, or RTH, that is V0 upon I0 is equals to 4 by 3, that is 1.33 ohms. So this is the answer. RTH or Norton resistance is 1.33 ohms. Now let's solve another question. Okay, so we have to find the maximum power that can be transferred to the load RL. Okay, so This is your load resistance RL, and let us draw the circuit first of all. So this is the source which is 4 angle 0, and this is given as RMS value. Okay, so it is 2 ohms, and this has impedance of 2j ohms. So these are the two terminals A and B where RL is connected. Right now, if we find the equivalent of the circuit, this circuit between terminal A and B, then we can see that VTH is equals to VAB. That can be easily calculated by voltage division rule, 2J upon 2J plus 2 multiplied by 4 angle 0, that is J upon 1 plus J multiplied by 4 angle 0 degrees. Okay, so if you solve this, then you will get that it is equals to 2.828 angle 45 degrees. So that is your VAB, or that is equals to VTH. Also, if you find RTH, now to find RTH or the resistance between terminal A and B, we will first of all short circuit this independent voltage source, and we can see that RTH will be equals to 2j ohms parallel to 2, that is 2 into 2j divided by 2 plus 2j. So this will come out to be 4j upon 2 plus 2j, or 2j upon 1 plus j. That is your RTH, or I can say ZTH rather. Okay, equivalent impedance, so ZTH, that will be a better expression. Now between A and B terminals, this whole circuit can be represented by a series combination of a battery, or I can say a voltage source that has value 2.828 angle 45 degrees, and impedance ZTH, and RL is connected here. So here we know the value of the voltage input, we know the value of ZTH. Now we have to find the value of RL for which maximum power transfer takes place. Now here I will explain you the 4 possible cases for maximum power transfer. Okay, so that will be a complete concept for the maximum power transfer. Okay, so we have case 1 where we have a voltage source Vs, Rs and RTH, RL, sorry. So here the maximum power takes place when RL is equals to Rs. Okay, so we know all this, we know this case very well. Now let's look at case 2 where, so I will have to add pages in this. Okay, so let me case 2. So here we have Vs as the source, but the impedance is Zs, that is Rs plus jXs, and we have load, that is RL and jXl. So in this case, for maximum power transfer, I keep RL as variable and jXl as a constant. So we have to find the value of RL for the maximum power transfer taking place. Okay, so in this case, value of RL for maximum power transfer is XL plus XS whole square plus RS square. Okay, now let's look at case 3, where we have source voltage Vs, impedance of the source is that is Rs plus jXs RL plus jXL. Now here let us assume that for maximum power transfer, XL is variable and RL is a constant. So here maximum power transfer takes place when XL is equal to minus times of XS. Okay. Now the last part, case 4. So here we have okay. So here we have both RL and XL as variable. So both are variable. So here we have RL is equal to RS and XL is equal to minus XS, or I can say that ZL, that is equal to RL plus JXL, is equal to ZS conjugate, that is RS minus JXS, for the maximum power transfer. So this can help you. These are the 4 possible cases. No other case is possible for the maximum power transfer. Okay, so in this case, in the question that is given to us, we have only RL in the load. So we have this case, that is case number 2 in the question. Okay, so let me redraw the circuit. We know that the supply voltage was 2.828 angle 45 degree. The ZTH or the Z impedance was 1.414 angle 45 degree, and this is your RL. Now since for maximum power transfer here, since RL is a variable, so that is equals to XL plus XS whole square plus RS square. Now since XL is 0, so that is equals to RS square plus XS square, that is equals to the magnitude of the impedance, that is 1.414 ohms. That is your RL for maximum power transfer. Now we can easily find the value of current in this loop, that is equals to the supply voltage divided by the total impedance, that is 1.414 ohms plus 1.414 angle 45 degree. Now using the calculator you can easily get the answer, that is 1.08 angle 22.5 degrees, that is your current. And the power transfer will be magnitude of current square into RL, that is 1.08 whole square into 1.414, that is 1.649 watts. Okay, so this is the answer to the question. Okay, now let's look at another question. So this is the question. Here it is given that we have to find the value of the angular frequency omega so that the Norton equivalent resistance is purely resistive. Okay, so this is the circuit given to us. Now since in the circuit there is no independent source, sorry, there is no dependent source, we can see that there is no dependent source, but there is one independent source So to find our BB dash, we will first of all short circuit this voltage source, short circuit the voltage source, and the circuit will be simply 1 ohms, 0.5 Henry and 1 farad capacitance with a B dash. Now we convert it into the omega domain, so or we will convert it into the impedances, so it is 0.5 j omega and it is 1 upon j omega B dash, 1 ohm resistance. So the impedance between BB dash is 1 upon j omega plus 1 parallel with 0.5 j omega, that is 1 upon j omega plus 0.5 j omega upon 1 plus 0.5 j omega. Okay. Now if I want to separate all the imaginary terms, because we need the value of omega where the imaginary term of ZBB dash is 0. So this is minus j upon omega, and I will multiply and divide by 1 minus 0.5 j omega in this whole expression. Okay, so minus j omega minus j upon omega plus, so the denominator will be 1 plus 0.5 omega whole square. Okay, and in the numerator it will be 0.5 j omega plus 0.5 multiplied by 0.5 omega square. So the imaginary terms, or I can say that the imaginary part of ZBB dash will be minus j upon omega, or I will take j as common. So j as common, minus 1 upon omega plus 0.5 omega upon 1 plus 0.5 omega square. So this term has to be 0. Okay, so this implies minus 1 upon omega plus 0.5 omega upon 1 plus 0.25 omega square is equals to 0, or 0.5 omega divided by 1 plus 0.25 omega square is equals to 1 upon omega, or from here I can say that 0.5 omega square is equals to 1 plus 0.25 omega square, or omega square is equals to 1 upon 0.25, or omega is equals to under root of 4, that is 2 radians per second. So at 2 radians per second the ZBB dash will be completely real. Okay, so let's finish this part here itself, and we'll be continuing solving the previous year network theorem gate questions in the further parts. So thank you guys, keep sharing and stay tuned.